Good morning, good afternoon, or good evening, depending on where you're listening from. Thank you very much for coming to this session today entitled Making Space for Spatial, Applying Doctoral Skills to the Climate Crisis. This whole session is run by the Geospatial Systems CDT and the Sense CDT. And I will talk a little bit more in a second about the overall structure of this session. This particular section aims to introduce the Geospatial Systems CDT, but more on that on the next slide. My name is Sam Cristello. I am a University of Nottingham student in the Geospatial Systems CDT in cohort 2, and I would like to thank my colleague Clara Pere Garcia, who put together these slides today. Together, we have curated this whole Making Space for Spatial session, so big thank you to Clara for all of her help. I will now go over the overall session structure in this next slide. Now, the overall structure of this Making Space for Spatial session. This will be divided into 3 distinct portions. Firstly, 2 approximately 15-minute long presentations introducing the 2 CDTs curating this session. The first, and that is this presentation that you're watching right now, will be an introduction to the Geospatial Systems CDT, hosted at Newcastle University and the University of Nottingham jointly. And following this will be an introduction to the Sense CDT, which is jointly hosted between the University of Edinburgh and the University of Leeds. Following this, we will have 4 student presentations of approximately 10 minutes each in length. Now, each of these will be delivered by a student from one of the CDTs. In fact, we have all 4 academic institutions represented in these student presentations. These presentations will focus on the skills that the student has acquired so far in the doctoral process, the technologies they're using, which might feature programming languages, cloud computing, etc. Obviously further details in the presentations themselves, and bringing all of those things together to be applied to climate or climate adjacent research. Now, we gave free rein on the topic of these presentations, but as long as it was a focus on some kind of work that they have been doing in the CDTs, so I think those will be really interesting for you. Finally, we have curated a panel discussion featuring both students and academics, with academic staff coming from Newcastle University and the University of Nottingham. That panel was chaired by me, so if you want to hear more from me, give that one a listen too. I think we discussed a really nice variety of questions there, and I think that'll be really interesting for you to listen to. So now on with this session itself, the introduction to the Geospatial Systems CDT. The Centre for Doctoral Training in Geospatial Systems is funded by the Engineering and Physical Sciences Research Council, the EPSRC, one of the UK research bodies that funds scientific research within engineering and the physical sciences within the UK. Now, in 2019, the EPSRC funded 75 centres for doctoral training in the UK, and one of them was in Geospatial Systems, with the aim of filling in the existing skill gap in the UK of people with geospatial skills and specifically with geospatial data focused skills. And the CDT has been running since 2019. It's a joint venture between Newcastle University, the true host institution, and the University of Nottingham, as well as around 40 industrial and academic partners. We'll talk a little bit more about that later. And the CDT has enough funding for around 50 doctoral students, with intakes being between 2019 and 2023. So far, 3 cohorts have been taken in to the CDT, with more to come in the following 2 years. The CDT follows a cohort system, but it's designed to not be segregated. So as much as students choose a host university either at Nottingham or Newcastle, there is a strong element of collaboration between the 2 institutions, and both horizontally within your cohort across institutions and also vertically with people who have come into the CDT before you or are coming in afterwards as well. That's very strongly encouraged, and I'll talk a little bit more later about the different ways that collaboration is encouraged. I think I speak for every student within the Geospatial Systems CDT when I say that we would be nothing without the staff running the whole show. We have a variety of staff associated with the CDT in different levels. The whole thing is controlled by a program management board of several staff members who regularly meet to discuss the running of the CDT. I've put up some lovely pictures here. I don't have time to run through everybody today, but perhaps some important ones to pick out would be in the top left, Professor John Mills, the CDT director, who's based at Newcastle University, and just below that, Professor Stuart Marsh, the Nottingham director of the CDT. If you want a few more familiar faces, you can see second from the left on the top row is Professor Dorian Boyd from the University of Nottingham, and at the bottom row, also second from the left, Dr. Alistair Ford from Newcastle University. Now, both of these academics very kindly gave up their time to appear in our panel discussion coming up later in this session. So if you'd like to hear more from them on some pressing issues in geospatial and how the doctoral process is applied to the climate crisis, then please do give that a listen. You'll be able to hear both of their thoughts on the topic, and I'd like to extend another thank you to them for giving up their time for that. Also, big shout out to top right, Jamie Stogden, our CDT manager. Nothing would happen without him. He's the grease on the wheels that keeps everything going. So big thank you to Jamie as well. The Geospatial Systems CDT has so far taken in 3 cohorts of students, and you can see some lovely pictures of our students here. We have students from a diverse range of academic and cultural backgrounds. We have people interested in things like transport planning, to Earth observation, smart cities, and everything in between. We have people with backgrounds in industry, people who've come straight from undergraduate degrees, people who've come from research assistant positions, and we have people with backgrounds in social sciences, economics, a whole range of things. And I think it's fair to say that we all get on really well with each other. We've had many chances to meet, particularly cohorts 1 and 2. I've met several times, and cohort 3 just coming in, we're just getting to know them as well. And so far, it's been a really, really great environment, and I've very thoroughly enjoyed my time as a CDT student. If you are particularly interested, that's me in the top right there. That's a fairly old picture taken in the bathroom of my old house during lockdown, when I needed a new LinkedIn picture. And I think the less said about that, the better. The final piece in the puzzle for the CDT and Geospatial Systems is our industrial and academic partners. We have a wide range of both, and there are a few names here that I'm sure you'll see. The UK government's Geospatial Commission, the European Space Agency, ESRI, even the University of Leeds, one of the hosts of the SENSE CDT, which you'll be hearing about in a minute. The Nature and Environmental Research Council, one of the UK government's other research councils, they're a partner with us as well. And perhaps most relevant today, KTN themselves. You can see their logo on the right-hand side of the screen there. The hosts of this Space and Geospatial Pavilion, they indeed are one of our partners. All of the CDT students are invited to engage with our industrial partners through a series of annual events, which I'll talk more about later, also through regular seminars that we receive from industrial partners, where they can be invited to come in and talk about perhaps the work that organisation does, or some interesting projects they've got going. We're also encouraged to seek out placements and academic secondments with these partners, and we have a dedicated industrial liaison officer within the CDT, Dr. Max Wilkinson, who his job role is to support us in that and help with industrial engagement during the CDT. It's come to the point in the presentation where I can hear you asking, well, this is all well and good, Sam, but what is a geospatial system? Well, I'll have to answer this in 2 ways. Firstly, the definition of geospatial that I tend to use personally is anything, well, a geospatial problem is anything that varies with time or with space. Now, I understand that covers a huge variety of things, but that explains why we have a huge variety of backgrounds and research interests here in the CDT. But what actually is a geospatial system? A geospatial system is founded on locational, so spatial data, and then through a process of capturing that data, managing it, analyzing it, perhaps modeling it, or even visualizing it and helping decision support in that way, using one or in most cases a variety of these techniques, on that locational data to form an integrated digital approach, which you can see at the top of the diagram here. Now, this integrated digital approach will be solving this geospatial problem. So from your foundation of locational data, processing that locational data to form, and again, this is key, an integrated digital approach. It's not going to include just one of these aspects. It's going to include many, or in most cases, all of these second layer aspects. And in the CDT, we are trained to form these integrated digital approaches to geospatial problems. The CDT has 5 research themes, which are spatial data capture and interpretation, spatial statistics and mathematical methods, big data spatial analytics, spatial analysis and modeling, and visualization and decision support. Any research proposed and conducted by the students within the CDT is expected to fit into one or more of these themes, and we have students conducting research across all of these themes, and indeed you can move between them, and a lot of research isn't really going to be focused on just one of these. It's going to be spread across several, often spilling over as the project continues. Students are trained in what is referred to as a 1+3 model, where we do a 1-year MRes qualification at the start of the programme, which is followed by a 3-year PhD course of research. This first year consists of technical training in the topics shown on the screen here, and throughout the whole 1+3, giving 4 years training program throughout the course, we are also given training in industrial linked activities and professional development. This professional development encompasses responsible research and innovation training, and also leadership, innovation, and enterprise training. Now, this is given regularly throughout the course within the first year, but carried on within the subsequent years as well. For our industry-linked activities, we have an innovation festival focusing on our industry partners every year. We have a challenge week where all the cohorts are brought together, given a problem, and given 4 days to work on that, and then present their solutions at the end. And we also have a yearly group project for the first year students in that first MRes year, which I'll talk about a little bit more on this next slide. Each year, first year students are assigned a group project within the CDT. One of our partners puts forward a problem, and in small teams, the students are expected to solve it over a period of a few weeks. This year, the partnership was with the Vinderlander Charitable Trust, who set the question, how can geospatial expertise contribute to the monitoring of the archaeological deposits at the Roman fort of Carvoren along Hadrian's Wall? And through the application of geospatial techniques, the 3 groups that we were split into produced a variety of different solutions. It's hard to condense 3 to 4 weeks of work into one slide, but that's what we've attempted to do here. I think the most impressive output from this year's group project was that the group you can see on the left here were actually able to publish their results after being deemed the most successful. And I think that was a great success for the CDT, particularly for students within their first year of training. Getting a publication under your belt was a really, really nice opportunity, and something that I look forward to seeing that same success in cohort 3 coming up this year. As we come towards the close of this presentation, I think it would be nice to highlight a few research topics currently being undertaken by students within the CDT. So I think one interesting one is the development of low-cost sensors for environmental hazard monitoring. So using technologies such as Raspberry Pis or Arduinos to form these low-cost, easily deployable sensors, which can then monitor changes in the environment, often changes linked to the climate crisis, which fits in very nicely with this whole virtual pavilion event. Or indeed to touch on some of my own work, which sort of fits into this idea of using Earth observation data for environmental change monitoring. Now, you'll hear a bit more about this topic in our presentation from Rebecca later on in the session, and also from the students from the SENSE CDT, whose work is focused around Earth observation. Thank you very much for taking the time to listen to this rather brief introduction to the Geospatial Systems CDT. If you have any further questions, you can feel free to direct them to Jamie Stogden, our CDT manager, at the email address below. And if you'd like to know more, please do check out the Geospatial Systems CDT website. I have been Sam Cristello, and thank you very much.
Hi there, my name is Ruth Amy, and I'm going to talk to you today about SENSE, the Centre for Doctoral Training Programme. SENSE is a PhD programme, and what a PhD is, it's after you've done an undergraduate degree, you can go on and do a research project. So this is 4 years long, working with academics at a university and finding out something new, something no one else has ever found out before, through independent research. The SENSE is a PhD programme, particularly we're a Centre for Doctoral Training. And what that means is we're a collection of students who are doing PhDs, where every single topic that all the students are working on is Earth observation. So this is satellite data to look at the Earth, and advanced data techniques. So these are new and exciting ways to probe the data and find out something new from it, including machine learning, artificial intelligence, and things like this. And we have 16 students per cohort, and will be 15 total. And these students are based across the University of Edinburgh, the University of Leeds, the British Antarctic Survey, and the National Oceanography Centre. We are funded by NERC, the Natural Environment Research Council, the Universities of Edinburgh and Leeds, as well as the UK Space Agency, as well as funding for our students from our industry partners. We have a large number of industry partners, and we're really pleased with our connections with them. And what they do is they provide partnership for individual students' projects. They might be co-supervisors, they might provide training or give access to facilities or data. So there's lots of ways in which we interact with industry. You'll see at the bottom the logos of all of our partners and funders. So SENSE has a unique feature as a PhD programme, a collection of people working on similar projects. One is the cross-discipline nature of all of the projects and the cross-institute supervision. So all of our PhD students have academic supervisors at a number of different universities and organisations. We give our students a very intensive training programme. So you'll see here at the bottom the icons for the kind of training that we give. And this is in satellite data and geospatial skills. And the idea behind this is that our students come from different backgrounds, but through this broad training programme, we're able to give them all a flavour of many different types of satellite data, many different geospatial skills that they can use to interpret and analyse this data. Another unique feature is, as I mentioned before, that we really engage with industry, and that all of our students will do a 3-month placement in industry, working with someone interested in the space sector, so that they can use their skills on something different from their PhD in a different way. And this will give them a flavour of the kind of thing that they might like to do in their future career, whether it be academia or industry or journalism or working in policy, a range of things. To give you an idea of the kind of things that our students are working on, so we currently have two cohorts of students. And you'll see on the right a host of different satellite data that our students are using, and on a whole variety of different topics. So from the solid earth to forests and crops, vegetation, to the atmosphere and ocean, the ocean and cryosphere, icy things. So there's a range of different topics to use. I think what's really exciting is that our students often can use very similar skills, even if they're working on completely different areas. So someone who's looking at the atmosphere might use a similar skill set and geospatial skills as someone who's looking at the solid earth, even though someone looking at solid earth satellite data might find the atmosphere something they need to remove, whereas one of our other students, that might be what they're interested in, but similar skills to different topic areas. You'll see as well at the bottom the flavour of our industry partners who support our PhD students in this first cohort. In our second cohort, we see similar things, some of the same satellites and some new ones, offering a whole new host of data, but again, a very similar skill set in order to investigate this. And again, a range of topics, so atmosphere, cryosphere, weather, oceanography, vegetation, ecology, all sorts of different subject areas that our students work on, many of which are directly related to climate and the climate crisis. Again, we have our industry partners at the bottom, some familiar faces from the previous page and some brand new ones. And if you look at this word cloud, which is kind of giving an indication of the kind of PhD titles, the projects that the students are working on, and you'll see overwhelmingly satellite data is coming out front and foremost. as well as the kind of topics people are working on. So the Antarctic, water, ice, glaciers, oceanography. This is the range of things that our students are doing. So more about our students, here are their smiling faces. We're so proud of them and the work that they're doing, particularly starting their PhDs during a global pandemic. They've done so well, and I really can't shout enough about how brilliant they are. So they've come from a whole range of undergraduate degrees. So they might have come from something like geography or earth sciences with very specific knowledge of glaciers or forests, or instead they might have come from physics and maths with very technical skills, but might not have subject areas. But all of these different disciplines have come together, and the idea behind SENSE is that we really provide training so that no matter what your background is, whether you've looked at many satellite images or never seen one before, we'll teach you how to do that and give you the geospatial skills that you need in order to do your PhD and to think about environmental problems and solve them and find out new things that no one else has found out before in order to do that. Our students have come from undergraduate degrees and master's degrees and from industry. So there really is a whole range of different backgrounds seen in our students. To give you some of SENSE's success stories, so one thing that we've done is we have this intensive training program. We were really pleased to open it out to other PhD students to join, and this offered a whole host of things, different talks and training, and finalised in the students designing their own satellite missions. So you can see a proposal here, carrots, look forward to finding out if this satellite is ever launched one day. Another thing that SENSE has done is hosted undergraduate interns. So last summer, we had a host of PhD students working with academics across the SENSE institutes. And again, this is very often the students' first chance to get their hands on some satellite data and interpret it. We're very proud of our links to industry, and we had a wonderful industry symposium for the first time this year. There were many interesting talks and panel discussions, and so I encourage you to go on our website and find out more about this. And again, all of these stories you can find out more about on our website. We're also very passionate about encouraging anyone and everyone to be a scientist. So we really think that anyone can be a scientist, anyone can do a PhD. And what we've done as part of our recruitment is put on webinars and produce materials to help support people apply. So even people who've never heard of a PhD and might not understand how their skills are applicable, with our webinar, they'll have support to understand how to apply and also find out why they should apply. We have a wonderful webinar on how can a PhD help me in my career, to find out the kind of things that people have done after their PhD that some cases are in academia, but in many cases aren't, and really finding out how the skills that people learnt, both geospatial skills and soft skills like presenting and talking to people and communicating science, and how they've helped all these people in our future career. So do go listen to those again, they're on our website. Another thing that our students are really passionate about and we really support them with is outreach and science communication. So they really want to talk about the science that they're doing and the environmental problems that they're studying and communicate this to children and to the wider community. This is a speech that they've done a series of things, including being the headline act at Leeds' Be Curious Festival. This was live from the Space Shed. You can go and see it on YouTube. They speak to children who are working with satellite data. They ran a successful Twitter campaign highlighting women in science and how they inspire them. So a whole range of ways that our students are really passionate about talking about their science and sharing what they're doing. And finally, I'd like to link us back to climate change and the climate crisis. So there are so many different projects that our students are working on and really thinking about climate from many different angles. So I've put up just a selection of the many things that people do here. So thinking about future food production and how crops will be affected in a warmer climate. People are looking at the impacts on glaciers and ice shelves, thinking about air quality, thinking about how savannas and dry forests will react in a different climate, looking at ecology, how it impacts whale strandings and penguins, and how humanitarian mine clearances are affecting the amount of carbon being stored. So this is just a touch on the kind of things, the environmental problems that our students are working on. But I'm going to leave it here. You don't want to hear from me anymore. It'd be much better to hear from the students themselves and what they're working on. So please do enjoy the rest of the session. If you want to find out any more about SENSE, if you're thinking about you'd be interested in doing a PhD with us or an internship or collaborating in some way, maybe you're an industry partner and you're interested in supporting one of our students, please do get in touch, look on our website, and we'd be really happy to talk more. So thank you very much for listening, and do enjoy the rest of the session.
Hello, my name is Neil Sutherland from the Geospatial Systems CDT at the University of Nottingham, and welcome to this talk looking at cloud computing and climate change, exploring the use of Google Earth Engine for monitoring the Scottish Flow Country. This presentation forms a part of the Making Space for Spatial focus group at COP26, and will explore applying doctoral skills to the climate crisis. So firstly, welcome. It's really exciting to be able to share not only some of the research that I've undertaken at the Geospatial Systems CDT, but really to elaborate on the ways we're being trained as doctoral students and how we're being encouraged to view challenges relating to all things spatial. So that, I suppose, is an important place to start. You know, what is spatial? And this is something we regularly debate within the CDT, often with varying definitions. But one thing that we always agree is that spatial is remarkably broad in its scope and applications. And this breadth is arguably due to how diverse spatial data is, not only including what could be defined as traditional, largely geo-referenced data, but now we're seeing the emergence of new data streams that are, in contrast, exploiting geo-related data. And these data streams of considerable volume and velocity now, when combined with advances in AI and computing power that we're currently seeing, provide the means to address the real-world challenges of today. And this is what our CDT has been set out to do, to help us have the knowledge, the technical skills and innovation to transform our understanding of an increasingly complex world. It's exciting to have this opportunity to demonstrate how the training we're receiving is enabling us to approach the goals of COP26 with the skills required to transform our research into effective solutions. So it seems that three main questions arise that need to be answered to understand how spatial can be used for positive change regarding climate issues. Firstly, why make space for spatial? As discussed, what is it that spatial can provide to established narratives to help combat climate change? Secondly, how can we exploit geospatial technologies to monitor and mitigate climate change? What are the trends of geospatial tech? What can we do with the vast quantities of data we have at our disposal? And finally, how do we approach problems uniquely from a doctoral perspective? What skills are going to be important to effect meaningful change? And arguably, most importantly, how do we communicate our research effectively? And to explore these questions, I'll be presenting some research I've undertaken looking at how peatland mapping can utilise Google Earth Engine to inform policies so that landowners and land managers can sustain the benefits of peatlands while maximising responsible use for future generations. The effective monitoring and management of peatland ecosystems is fundamental in our fight against climate change. Peatlands such as those covering the Scottish Flow Country span just 3% of the Earth's surface, but actually equates to 30% of our terrestrial carbon stocks, more than twice that stored by all forests on Earth. These peatlands generate invaluable ecosystem services, including remarkable biodiversity, irreplaceable wildlife habitats, whilst also providing considerable socio-economic and cultural value. However, drainage, peat cutting and afforestation have led the Scottish Government to determine that 80% of the flow country is degraded or in need of restoration. So, in the face of mounting urgency to restore these landscapes, research acknowledges that comprehensive long-term monitoring is critical in the conservation and restoration of peatland ecosystems. So, how can spatial shed light on this issue? And what developments have allowed spatial to become central to monitoring global wetlands? Well, firstly, we've seen increasing access to spatially and temporally rich open source geospatial data, which has been pivotal in supplementing in situ peatland measurements, allowing greater areas and time series to be assessed. Furthermore, we've seen key developments in computing capabilities over the past decade that makes the analysis of this data far more manageable. Google Earth Engine, introduced in 2010, is a cloud computing service that allows planetary scale analysis that exploits this vast amount of geospatial data through parallel processing. Within Earth Engine are numerous integrated machine learning functions that enable stakeholders to determine tasks and execute solutions, which is why we're seeing Earth Engine's increasing use in climate-related research. But why is this? And arguably the most noteworthy features of Earth Engine is that it provides expert and non-expert users with the ability to access and analyze this data, regardless of computing power or expertise. Appreciating that the challenges posed by climate change necessitate multidisciplinary teams, Earth Engine has the ability to integrate vast amounts of spatial and non-spatial data that can be visualized and shared with remarkable ease. So, what does an Earth Engine workflow look like, and how can it be tailored to tackle various climate challenges? The work I undertook looked to classify an area of the Scottish Flow Country based on several classes, classified relating to land use and land cover type. These classes were central to two of Scotland's key climate policies, the Land Use Strategy and Update to the Climate Change Plan, which outlines the ways in which Scotland will adapt to the targets set out by the Paris Agreement and reach net zero by 2045. To accurately classify land based on its inherent characteristics, research suggests that a combination of optical, radar and topographic data is fundamental to comprehensively map peatland ecosystems. And that is what Earth Engine provides, a platform to quantify and project climate changes by accessing and analysing numerous geospatial datasets. Specifically, this work used Sentinel-1 synthetic aperture radar, Sentinel-2 multispectral imagery, and NASA DEM datasets, along with several derived indices, to compute input features for a random forest algorithm. This classified an area of the Scottish Flow Country and can now provide context to the desired changes set out by the Scottish Government. So, what can the results of Earth Engine studies provide us? And how can geospatial technologies enhance our understanding of our pressing climate challenges? Well, firstly, Spatial is providing the means to examine wetland landscapes and their inherent features in greater detail than ever before. And by exploiting Earth observation and remote sensing data, we're constantly finding new ways of understanding how climate change is affecting both peatlands and their biodiversity. And with ever-increasing access to improved datasets, algorithms, and functionality, Earth Engine can enable analysis to be more intuitive and helpful in determining strategies and policies to tackle climate change. Earth Engine allows for work to be constantly amended, enhanced, and shared, with all users able to develop projects concurrently and implement findings. The development of the methodology showcased here has determined an amendable workflow for evaluating policy targets and deriving products such as land capability and suitability maps, calculating carbon stocks, and determining areas for targeted intervention. So, to review the questions we sought out to answer, why make space for spatial? Well, spatial is providing the means for us to tackle climate change with increasing amounts of data that provide invaluable perspective to our most pressing challenges. We're able to utilise geospatial data not only to understand the current state of our planet, but also how we design a sustainable future by integrating this data into our everyday lives. Geospatial technologies are allowing us to collect and analyse data in ever-increasing quantities, and advancing the way we model and present this data will be paramount for confronting the climate crisis as it evolves. And finally, as doctoral students, we're constantly being encouraged to seek out these trends, assess how spatial can provide a new means of addressing existing or future challenges, and ultimately communicate these findings, and generate meaningful deliverables for our collective fight against the climate crisis. Thank you for your time and the opportunity to share some of the work of the Geospatial Systems CDT. I hope you enjoy the rest of COP26.
Hi, I'm Sam Bancroft. I'm a PhD student at the University of Leeds, part of the Centre for Satellite Data and Environmental Science. My PhD project is all about assessing future food production using satellite imagery. My presentation today is actually going to be about why and how people use remotely sent satellite data to solve the pressing food security questions of today. To begin with, I'll start with this signal from nature, this plot. This red line shows an average time of the year that the cherry blossom in Japan has reached its peak blooming. I find this as a particularly unique set of observations. We're very fortunate enough to have this set of human records stretching back to the year 812. And what this shows us is that the average peak bloom date was relatively stable for about 1,000 years, all the way up to the year 1800. But beyond that date, the peak bloom dates get earlier, and it reveals a shift that is getting earlier and earlier in the spring. Now, this is really interesting. Some of the warming, some of the early flowering events are due to climate change, and some are also likely due to an enhanced heat island effect due to increasing urbanization of the environment over the last couple of centuries. But evidence, like the timing of Japan's cherry blossoms, are one of the historical measurements that scientists look at for signals that our climate is changing, and also changing much more dramatically than it has for a long time. This is a signal from nature, stretching back in history, and it tells us about the unprecedented human-caused warming of the planet that we're witnessing today. To give us some context, some background when we look at food security, the world's population is expected to grow by a third by 2050, most of this increase in developing countries. And that in itself puts a lot of demand on water, it puts a lot of demand on land, and also demand for food. The demand for food is expected to increase by about, ranging from 59% up to 98% in that same amount of time. Now, 2050 is not that far away. In addition to all of this, a changing climate poses significant challenges to the yield of our crops and the long-term suitability of where we can actually grow these crops. And all of these issues driving up demand for food, and it means that the world's agriculture will have to transform more radically than it ever has before. We need a lot of change, and we need a lot of change quickly. Right now, we're facing a problem of global scale. We know that the world's food systems are profoundly affected by climate change, from how we produce our food to what food we can grow in the first place. Climate change will hit our food production system in many ways, including temperature, water, extreme weather events, and pests. Crops will feel the impacts of temperature first, whether it be due to rises in the mean temperature, chronic heat stress during the growing season, or more episodic heat stresses at a particular point in a crop's growing cycle, for example, the flowering period. Climate change-induced temperature increases will have quite a big effect on overall reductions in net global crop yields. When it comes to water, agricultural revolutions in history have boosted food production beyond what many thought was possible, feeding billions more people than ever before. This is associated with improvements in water supply due to, for example, improved irrigation. As climate change contributes to increasing water scarcity, though, these innovations may turn out to be unsustainable, and that we can't use water to our benefit in the future as much anymore. Extreme events are forecast to increase with climate change. These can range from flash floods to gradually worsening droughts, making it harder to predict where and when the next large-scale crop failures will occur. And pests. Climate change increases the metabolic rate and the number of breeding cycles of insect populations. Currently, surprisingly, pathogens take about 10% of the global harvest already. This level will rise, particularly due to dramatic rises in insect populations in more temperate places and at higher latitudes. This can all get complex as everything is connected. Also worth remembering that agriculture contributes significantly to greenhouse gas emissions as well, about 30% of the worldwide total. The point is that climate change is set to leave us with less food that is less nutritious, also less nutritious due to the rising CO2 in the atmosphere. Over the coming decades, the changing climate and environmental stresses will have significant yet uncertain impacts on global food security. Areas which were historically good for farmland will no longer be as suitable. There is still uncertainty and therefore a lack of preparedness as to when and where the most significant impacts will occur to our crops. There are steps we can take to mitigate and adapt to these changes, and working out what these steps will be is the key to the future of the world's food production. Now, despite all these rising challenges, we do have the tools at our disposal to make sense of the challenges before us. When we think about the signals from nature that I talked about in the first slide, satellites already do an excellent job of doing things like this by assessing the global land surface. We have a historical view of how the Earth has changed through time. So you can see here an example of lots of deforestation in South America making way for agriculture over the past 30 years. We have a historical view of how the Earth has changed through time and what is in store for our future. But how exactly do we use satellites for agricultural monitoring and interventions? It is a really exciting time in Earth observation. There's a need for a new generation of satellites, such as the Sentinel program, the Copernicus program from the EU, and also the NASA Landsat program. These satellites do a particularly good job at measuring crops at the field scale through radar observations or by looking at what light is reflected back to us from the planet. These satellites are really useful for my PhD in crop type classification as well. They're really exciting because it's lots of open access and publicly available data. Anyone can download and access this information. If data on crops through satellite data is known, it can be used to support informed decisions on how best to manage the land. Applications, there are many applications from crop yield estimation and prediction to disaster impact assessments. Policymakers, stakeholders, importantly farmers, all of these groups rely on detailed, spatially explicit information about land cover in agricultural areas. But what can we measure and then change? Where can we plan our interventions? This is the power of the geospatial data, this continuous and reliable source of satellite data about where and when things are happening. So to begin with, cropland classification is one of the most used information to manage and plan many agricultural activities. You can see in the bottom left different crops in a European setting being classified, particularly potatoes in the fields. Now, you can achieve this with ground surveys. Farmer surveys and in situ measurements can be conducted to gather data about crop type and yields at the farm level. But that's really overwhelmingly expensive and really intensive task when you consider the large scales required. This is something that is achieved through satellites at a much, much cheaper cost. Once you know where the crops are, you can do a lot about field characteristics, about soil health, tillage practices, how things are being irrigated, how the land is being managed. You can look at specific crop types, and you can also feed it into models to look at crop yields, both decades into the future and also at the end of the present harvest. I think remote sensing can reveal impacts at scale really well. So here's a nice example using satellite data looking at tillage intensities, and you can look at that with satellites. You can also look at crop yield. So here's both a similar area in North America being looked at in terms of field scaled yields and also field scale tillage intensity. And then you can do really exciting stuff like combine that, and then you can see what effect the tillage has on improving crop yields. So this information can tell us that after about like a 10, 11 year timescale of conservation tillage and efforts to reduce soil erosion in croplands, it can have an overall positive impact on our crop yields, and we can prove that. I can also see where it's most useful to apply this, these farming practices, and where perhaps it might have a negative impact on yield instead. You can look at that spatial distribution and cover really interesting effects. Something that also happens now is global collaborations. This is the GeoGlam group looks and facilitates a lot of satellite data and observations to look at a worldwide view of crop conditions. These are the crop conditions as of September this year, and they show where things are going well and where things aren't, and satellites are underpinning a lot of the information that we're seeing here. And there's so many more things that are going to come out in the next few years that will be really, really useful for us. So to summarize, food security is a hard thing to achieve in many parts of the world today, and it's only going to get much harder. But satellites have already documented large changes that have taken place worldwide. And geospatial data from satellites will help reshape agricultural markets in a way that we've not seen before. Farmers worldwide will have the data that they need to increase crop production and where exactly they should grow crops and in what ways they can enhance productivity on the existing lands. Increasing pressures on agriculture will jeopardize the ability of the world to meet its food production requirements. And yes, doubling our food production by 2050 will undeniably be a major challenge, but we can do something about it. After 10,000 years of temperatures that have varied only within about 1 degree Celsius, a period of stability, that's a climate where our food systems and our infrastructure have been built upon. But we're now on track for maybe upwards of 3 degrees of warming by the end of the century if we don't change course. We are now addressing our vulnerability to a level of climate disruption that human civilization has never seen before. We need methods of monitoring to make better decisions about our environment. The only way to do this in a continuous and a reliable way at large scale is by using satellites. We are in an era of abundant satellite data for any agricultural field in the world. It's a really, really good time to really make use of this rich data source. We cause the problem of climate change, but it is well within our ability to work to fix it and avoid a disastrous future. Thank you very much.
Hi, my name is Rebecca Gagney, and I'm a PhD student at the CDT in Geospatial Systems at Newcastle University. And I'm going to talk a wee bit about my research, where I'm using remotely sensed data from GRACE, or the Gravity Recovery and Climate Experiment, to monitor how groundwater resources are changing. And I'll hopefully highlight how geospatial and geostatistical techniques can be used to help towards meeting the goals of COP26. The 4 main goals on the agenda for COP26 are mitigation, adaptation, finance and collaboration. And my research ties in with the goal of adaptation, adapting to protect both ecosystems and communities from the inevitable impacts of climate change, many of which we are already experiencing around the world. Of these various threats of climate change to human health and livelihoods, the IPCC lists changes to the global water cycle as one of the most critical. The UN estimates that there are currently over 2 billion people already living in areas subject to water stress, and this is only expected to escalate. And much of this water crisis is hidden beneath our feet. Only 3% of the world's water is fresh water, and of the fresh water that is not locked up in glaciers and ice sheets, 99% of this is made up of groundwater. Groundwater is the primary water resource for billions of people, supplying half of the water used for irrigation globally, and on average, 1/3 of our fresh water supply. This varies depending on location, but particularly in some of the mid-latitude areas where much of the surface fresh water is drying up, this percentage can reach up to 100. And despite this critical importance for both water and food security, increased water demand, and because groundwater is somewhat an invisible resource, being underground, it is often avoided active management, and as a result, it is estimated that over 50% of the major global aquifers are being depleted. In particular, India is more dependent on water pumped from aquifers than any other nation, and the northwest of the country has emerged as a global hotspot, with studies showing some of the highest depletion rates globally. The Yamana Basin, the most western sub-basin of the Ganga, and the wider river basin that serves Delhi was the area that I focused in on for my research. Delhi is very much at the epicenter of the groundwater crisis in India. Its population already exceeds 31 million and is predicted to become the most populous city by the end of the century. This not only puts huge pressure on water resources, but also puts pressure on land use, which has resulted in unchecked urbanisation. This in turn can impact groundwater, as the more impermeable surfaces reduce the amount of water that can be recharged into aquifers. Then, on top of these anthropogenic pressures, climate change is very much intensifying the issue. with increasing temperatures increasing evapotranspiration rates, but also causing increasingly unpredictable and extreme precipitation patterns. So the relationship between climate and groundwater is actually quite complex and generally is not very well understood. Given this, there is need to both quantify how groundwater is changing in the area, but also understand the impacts of these interactions so to better manage the resource. But one of the greatest barriers for sustainable groundwater management is the ability to accurately map aquifer storage volume changes. Traditionally, this would be done via measuring the water table at wells. However, this method is limited due to sparsely distributed wells not being regularly maintained, but also issues with data access, particularly across political boundaries which many large aquifers span. But when GRACE was launched in 2002, it was a joint satellite mission between NASA and the German Space Agency. It provided the first satellite mission capable of mapping groundwater at large scales. The basic idea behind GRACE is that it maps gravity anomalies every month across the globe. Then from this data, you can infer how terrestrial water storage is changing. Then, by removing other surface water components that are generally quite well modelled, you can isolate the groundwater storage element. So my project focused on two main objectives. The first one was to quantify how groundwater levels are changing. So looking at the overall trends in groundwater storage from both GRACE and as observed in wells. Does this vary spatially over the region? But also another key aspect of using GRACE in this way involves validation of the satellite-based estimates against observed values and determining which of the available GRACE products performs better for this application in this specific region. I'll briefly describe an overview of some of the geospatial data used and the methods employed to answer these questions. Firstly, different GRACE data products were combined with modelled surface water components from the Global Land Data Assimilation System to isolate the groundwater storage estimates. Individual well observations were integrated with data on their specific aquifer properties to derive a similar comparable observed groundwater storage estimate. The two time series were then compared using comparison statistics to validate the GRACE estimates, and then a non-parametric trend analysis was carried out to assess both the temporal trends across the basin, but also the spatial trends, by performing the analysis over individual GRACE grids. This graph illustrates the basin-wide groundwater storage estimates derived from the different GRACE solutions, plotted against wells, which is the red line graph. In general, we're seeing really good agreement between all solutions, and you can see that GRACE demonstrates very similar fluctuations and has accurately captured the distinct seasonality of the region. Looking closer at validation statistics, we're getting high correlation across the board, but the GRACE mask-ons, which is generally considered a more rigorous processing approach, distinctly outperform the rest. Overall, these results indicate that GRACE very successfully captures changes to groundwater resources in this particular region, with the satellite estimates explaining up to 96% of the variation that we're observing in wells across the basin. By then performing this trend analysis spatially, we can see that all approaches are consistent in highlighting that depletion rates are not uniform across the basin. The northern regions are experiencing quite severe groundwater depletion, while parts of the southern basin have actually gained groundwater over the study period. Then comparing the different GRACE solutions, visually there's quite a stark difference as the different products have different resolutions. They solve for mass anomalies in different sized and shaped grids. But again, in general, mask-on solutions better match what we're seeing happening in wells. Then the second objective concerns investigating the drivers of groundwater change. So basically answering which factors have the largest influence on groundwater change, and does this vary over space? To do this, we looked at climate data, including temperature, precipitation, and potential evapotranspiration, and anthropogenic factors, including land use and population. By using these auxiliary data sets as explanatory variables to predict GRACE groundwater change, multivariate regression procedures and dominance analysis was employed to determine which factors were the most influential in predicting groundwater storage change over space. The first map here shows which of these variables had the greatest influence. Again, we're seeing quite a stark north-south divide, The northern regions, which have the most severe depletion rates, are influenced predominantly by anthropogenic factors, namely population change and an increase in urban land use. While in the southern areas, groundwater is influenced more by climatic factors, suggesting that increasing trends here might reflect the natural variability of monsoon precipitation. A further observation was that the region also varied in the predominant precipitation response. Different precipitation variables were tested in terms of the number of preceding months of precipitation, which had a greater importance. For example, total precipitation in the preceding 3 months and 12 months. And again, the results are showing an obvious north-south pattern, where the northern regions have a more lagged response to changes in precipitation patterns. Potentially, this could suggest areas which have greater resilience to climate change. In terms of the implications of this research for climate change adaptation, the spatial data and geospatial and statistical techniques employed can be used to improve both observation and understanding of the spatial and temporal variation in groundwater depletion, both in India and in other regions globally, which is critical to inform sustainable water management. This approach is particularly valuable in data per regions with very limited access to any alternative in situ data regarding the availability of groundwater resources. Moreover, the use of GRACE, an open source dataset that is available globally, further demonstrates the transferability of this approach. And results have also highlighted the complexity of the precipitation-groundwater interaction. Given the projected future increase in the variability of precipitation, this highlights that further research is needed to establish a more complete and comprehensive understanding of these dynamics, which will be fundamental to inform future water availability and plan to preserve and manage this essential resource in the future.
Hi everyone, my name is Morag and I am going to be giving you a talk about Cryosat-2, Arctic glaciers and ice caps in a warming climate. I'm a CDT PhD student at the University of Edinburgh and my main supervisor is Noel Gramelin. So today I'm going to be giving you a quick little context about what land ice forms are found in the Arctic and the Earth observation technique that I use to look at them and the climate trends that are being seen in the Arctic, and then how these kind of all come together to then look at different sea level contributions. So land ice found in the Arctic is in many different forms. We have the ice sheet in Greenland, but we also have glaciers and ice caps, so smaller land ice forms that are found in also in Greenland as well, around the edge of the ice sheet, but also in Canada, Russia, Norway, and Iceland. So in fact, there's 40% of the global glacier and ice cap ice volume is found in the Arctic. So this makes it a really good area to kind of study how these land ice masses are changing and what are causing these changes. So there are many different Earth observation techniques for looking at ice masses. So I use the Cryosat-2 European Space Agency satellite, and specifically I use the sensor that's called Cyril. So it is a radar altimeter. So I've just put it in a red box that, just to kind of highlight how it works. Essentially, it looks at the distance, and then when you look at that over time, you can then get an elevation change. So this radar altimeter allows us to see how the surface of the glacier is changing over time, and then you can then take this and turn it into a mass change. So as you can see in the figure, there's a couple of other methods. There's surface velocity and local gravity change. So both of these can also be used to gain a mass change as well. However, I'm just going to focus on the Cryosat-2. So the advantages of using a radar altimeter is that it is weather independent, so it can give you a continuous stream of data. It is also light independent, so in the Arctic you have 6 months when there is total darkness. So as you can imagine, the fact that the radar altimeter is not affected by this is a very good thing. That just means continuous data throughout the day and throughout the year. And also another advantage is the high resolution that can be extracted from the radar altimetry data. So this makes it particularly good for looking at the smaller glaciers and ice caps that are found in the Arctic region. A main disadvantage is that it has variable surface penetration, depending on whether on the surface there's snow or fern or anything in between. And I think this actually highlights my main point really well, is that when we get Earth observation data, all it is an observation. So just to maybe walk you through my point, here we have elevation change 2011 to 2014. So this is Cryosat-2 data off the Greenland ice sheet. And as you can see here, it shows us where there's an increase in height and where there has been a decrease in height in elevation. But what it doesn't tell us is why. So again, when we look at images like this, we have to be like, okay, there's possibility for, you know, variable penetration into the surface. So we need to take that into account. But we also need to take into account that there are many different processes that are occurring in an ice sheet and also on the surface of the ice sheet. So, you know, internal ice dynamics, but then also external phenomena such as, you know, there might have been snow fall in one region, or there might have been surface melt in another. So at the end of the day, Earth observation gives us an observation, but it is up to us as scientists to then use our knowledge of the area at a ground level, and also climate data sets, and all of this other information to actually kind of extract what is useful from these very, very massive data sets that these satellites produce. So taking us on to just maybe a bit more information about the Arctic region itself. So we spend a lot of money on looking and observing these ice masses. And I guess the question is why? So one of the reasons or justifications for my research is that the Arctic is currently experiencing warming at 2 to 3 times at a rate that's 2 to 3 times faster than the rest of the globe. So here's just this little temperature anomaly figure to kind of highlight that. As you can see, the hotspots are sitting over the Greenland ice sheet, you know, over the Russian Arctic. And this kind of increase in temperature, the effects aren't in the future. They are actually happening already. We are already seeing the Arctic region reacting to these increased and sustained temperatures. So a good way of kind of getting this information is there's an Arctic report card that is released. And for 2020, that was the second warmest year on record. It also had the second lowest minimum sea ice extent in the 42-year satellite record. So it's just to highlight that, you know, we are already seeing these changes. And then if we kind of draw this back to the land ice masses, well, we've got a massive ice sheet sitting under this hotspot, but we also have lots of smaller glaciers and ice caps, which are very sensitive to change due to their smaller size, sitting in these hotspots as well. And it is one of the main motivations behind understanding how these glaciers and ice caps react to these forcings, because in actual fact, their contributions are significantly bigger than the ice sheet. So just to kind of highlight that point, we've now come on to sea level rise. Here's a figure that shows the mass change and then also the sea level contribution of the ice sheets, which is in black, so the combination of the ice sheets compared to the glaciers and ice caps of the world. So even though the ice sheets hold a much, are much bigger, so therefore maybe might draw your attention a bit more, it's actually the smaller glaciers and ice sheets are having the biggest contribution. So in the Arctic alone, over 7 years, 2010 to 2017, they lost 609 gigatons of ice. So I mean, to try and put this in a way that is easy to visualize, a gigaton is 1 kilometer cubed. So 609 kilometer cubed of ice was lost. So that amount of ice is gone. It has been put into our oceans. That has already happened. So yeah, that's just to kind of highlight just kind of like the significance of the input of these like smaller land ice masses that are found in the Arctic, and then also why there is significant motivation behind using Earth observation in order to see how these glaciers react to forcing, in order to then gain more information about how they may react in the future, so that we can then input this information into our sea level rise models and hopefully make our projections more accurate. So then we can feed that information into reports such as the IPCC reports that get published. And then, you know, just to bring us, that links quite nicely to my next figure. So here we have a figure, this is off the Greenland ice sheet. So this was done by the INBI team in 2020. And as you can see, the sea level contribution of the Greenland ice sheet is following this kind of red projection line that's been put on. So this projection is from the AR5 report that got released and by the IPCC, and is actually for the upper CO2 emissions projection. So as you can see, we are following kind of the least optimistic projection for sea level contribution at the moment for the Greenland ice sheet. So that is how the biggest land ice mass is kind of reacting and is behaving at the moment. And I think, again, highlights the motivation behind not only wanting a greater understanding about how the ice sheet is going to change, but also how the much smaller glaciers and ice sheets are going to be reacting in the future as well. For if the bigger ice sheet, which is as we think at the moment, less reactive than the smaller ice sheets, then it is concerning for then how the smaller land ice masses are going to react. So hopefully, without having gone too much over time, I just want to summarize that the CRISAT-2 uses a radar altimeter, and this provides continuous observations at a high resolution. So this allows the smaller glaciers and ice caps to be observed and studied. And I also wanted to highlight that global warming, it is happening around the world. However, not every region is experiencing the same effects. And I just wanted to emphasize that the Arctic is experiencing amplified warming, which, as it is home to a large proportion of the world's land ice masses, is you know, of significant concern for us. So thank you very much for listening. I actually have a couple of links here. I don't know if you can screenshot that, but if you just want to get a bit more information about what I've been talking about. Thank you for your time.
Okay, hello everyone. Welcome to this panel discussion session being hosted as part of the Space and Geospatial Virtual Pavilion running alongside the COP26 event. This has been jointly organised by the EPSRC, CDT and Geospatial Systems and the UKRI Centres CDT. My name is Sam Cristello. I'm a cohort 2 student in the Geospatial Systems CDT, and being assisted today by my colleague Clara Pere Garcia, who is hosting the meeting and doing all the important things behind the scenes. I'd like to thank all of our panelists for appearing today, and if you wouldn't mind, I'd like you to just give a quick introduction of who you are, what you do, and what you're hoping to get out of the session today.
Hi everyone, I'm Sam Bancroft, part of the Centres CDT, and I'm a second year PhD student at the University of Leeds. The CDT is all about projects that involve a focus on Earth observation and data science, and my project in particular is looking at assessing future food production. And a big part of that is using deep learning and computer vision to look at where crops are being grown worldwide, particularly in developing countries with smallholder agriculture.
Thank you, Sam. I'm pleased to be here. My name's Dorian Boyd, and I'm Professor of Earth Observation at the University of Nottingham. And I'm one of the co-investigators on the Geospatial CDT. But I cross over into the 7th CDT because my background and expertise is in Earth observation. I also have the specific role of Director of Training within the CDT, and what we're doing here today is very much in line with that role. I'm very intrigued to hear what everyone on the panel has to say about skills and knowledge that we deliver as part of the CDT to tackle the particular issue of the climate crisis. And as I say, I'm really interested to hear what the students who are the heart of the CDTs have to say.
Hi everyone, thanks for the invitation to be part of this panel. My name is Alistair Ford and I'm a lecturer at Newcastle University and also a director of the Geospatial Systems CDT. And alongside that, I'm also a member of the Tyndall Centre, which is a UK network for climate change research made up of a number of UK universities. And it's really nice to be part of this panel tackling, I think, a really important topic of how the kinds of skills that are being learnt and delivered in the Geospatial Systems CDT can contribute to this really the global issue at the moment that humanity faces. I think, you know, this is such an important year and such an important event in COP26, and we all have a part to play, and I'm looking forward this morning to exploring what our particular part is as geospatial people.
Hi all, my name's Neil Sutherland. I'm at the Geospatial Systems CDT at the University of Nottingham. I'm just going into my 2nd year, which is the sort of PhD portion of the CDT. I have a background in sort of history and architectural conservation, so a fairly different perspective to the sort of Earth observation bunch. But yeah, I'm really excited to join this panel and discuss what makes the sort of doctoral process unique and how it can be a new way of really tackling, as Ali said, the biggest crisis of our time. And yeah, I'm looking forward to discussing this with you all.
Hi, my name is Alexandra Zakolemska. I'm part of the cohort 1 of Geospatial Systems CDT at Newcastle University. So my background is in remote sensing and more specifically vegetation monitoring. What I'm working right now at the moment are how we can monitor vegetation using local sensors such as Arduino or Raspberry Pi cameras, and looking specifically at tree health and tree stability to detect potential points where a tree can break and damage some part of infrastructure. What I'm hoping to get out of this panel is to actually maybe discuss this with fellow students and staff members, what further skills we can actually develop to help tackle the climate challenges in the future, and as well to gain a bit of more perspective from the staff members of what might be expected of us in the future as well as PhD students.
Brilliant, thank you all. I think you'll all agree that we've got a great panel here today. So just to briefly go over the aim of this session for any of our audience members who are watching, we're aiming to have broadly a discussion around the application of doctoral skills to the climate crisis, including the effectiveness of our training and the roles that our CDTs play in preparing us for our futures as doctoral graduates. And I think it'll be really interesting, as some people have picked up on already, to have both the student and the academic perspective. So you've got the people being trained and also the people delivering and designing that training. I think there'll be a really interesting balance to be had there. So we've got 4 prepared questions today, and we're planning to spend around 10 minutes on each one. The panel participants have seen these questions already, so don't worry, I'm not surprising anyone here. The first question, which I will just open up to the panel if anyone would like to dive in, we have titled, "What makes the doctoral process applicable to fighting the climate crisis?"
I'm happy to start off with an answer to that, Sam. That's a really, really crucial question. And of course, these centres for doctoral training are relatively young. So both the Geospatial Systems and the Sense centres were set up in the last few years. And of course, in a time where we're facing a crisis around climate change. And of course, we're sitting in a fluid environment, and just yesterday the Prime Minister announced the government's net zero strategy. Now there's all sorts of debate around net zero, but let's put that aside and applaud the fact that we're moving forward with tackling the climate crisis in some way. So the strategy sets out how the UK will deliver on its commitment to reach net zero emissions by 2050. So we could debate that that's not quick enough, but what's really interesting is when you read that strategy, it's really clear that a range of expertise and a range of skills are going to be required. And key to this is innovative thinking, understanding how new knowledge and approaches and methods are created, and how you go about establishing meaningful collaboration across many agencies and partners to face up to the task of climate change. And I see the CDTs very much as delivering that opportunity for students and staff to have that space to develop those skills and the personality and the confidence to move forward to tackle climate change. Climate change is cross-cutting in its issue and requires consideration within all strategic decision making. And so the skills of these CDTs must play a part in managing the economic transition that's going to be required. And so that requires the specific skills that you will all gain to give us that just transition, but also the sort of higher order and general skills that might sit outside your specific research area. So it's that general development as a person that will enable that just transition to net zero to happen. And I think what the Centre for Doctoral Training does is really does give you the space to be able to develop those skills, as well as that ability to become the expert in the particular topic that you'll be working on over the period of your time as part of the CDT.
Yeah, I'd like to follow what Dorian, I think, has covered a load of important points there. I think almost it's a real opportunity for you guys who are doing PhDs as part of these CDTs, because a PhD, well, it opens a lot of doors and it allows you to really go in the direction that you want to head in. So hopefully the training in things like responsible research and innovation that you get as part of a PhD helps you to think about, what are the research topics that I can apply my skills to that will not just benefit me as an individual, but will benefit society and the natural world, etc. as well. And I think climate change as a topic is so broad that it gives you really the opportunity to go in a huge number of directions. So we can think about climate change mitigation, so the emissions reduction part of climate change, which is all about the net zero strategy that Dorian discussed, that was announced recently. How do we decarbonize our society through technology? Yes, I mean, there are technological interventions that we need to think about, but also through societal changes, behavioral changes as individuals, and changes to the natural world, reforestation, rewilding, all of those kinds of things as well. But there's also then the adaptation angle of climate change, the resilience to the climate crisis that is unfolding and the changes that will bring, and how do we ensure that everyone on this planet has a secure livelihood and a safe existence, and that just includes humans. It includes other inhabitants of this planet too. So there's a huge range of potential directions that a PhD could go in that is around the climate crisis. in terms of technical skills and things that you could study as a PhD. But as Dorian also mentioned, I think there are these more transferable skills that you pick up as a PhD researcher that are also hugely relevant to tackling this climate crisis and this net zero announcement. I mean, one of the things that hopefully you learn as a PhD student is to think critically and to analyze. And quite often reading these kinds of documents, you know, if you have a critical eye and you're trained in thinking, you know, what does this mean? What is the data behind this? How is this backed up? Then a lot of these strategies and documents, you know, might raise a few eyebrows, and a lot of people have already criticized, you know, whether this is ambitious enough and whether this is anything new and lots of other things. So that training as a critical researcher, as someone who can, you know, read something, analyze it, and find the gaps in it, and then think, well, what do we need to do to improve this? I think is a really important set of skills to take away from a PhD as well. I'll stop there because I could go on all day.
No, that's fine. I think some very strong and I would say relevant statements there from both of our academic staff here. I think it would be great to hear what the students think of that. You know, a lot of focus there on the sort of critical thinking skills that you gain from a PhD and that maybe being applicable to the climate crisis. I wonder how the students on this panel feel. Do you feel that is something you have developed so far in your PhD program compared to, for instance, your undergraduate degree? Is that something that's significantly advanced and has that been helped by the CDT process?
Yeah, I think that's really interesting. I think picking up on what Dorian said, she used the term meaningful collaboration, which I think was really interesting and particularly important when we think about CDTs, sort of bringing, you know, cohorts of students together from different backgrounds. I think we're sort of encouraged from the off really to appreciate that we're approaching challenges in sort of collaborative, multidisciplinary ways. And I think obviously, you know, that's a huge part of COP26, with collaboration being one of the 4 COP goals. But yeah, I think we're encouraged from the very off that everything can be, you know, exploiting different expertise in different places, and that's something that we are reminded of through all the activities that we have throughout the sort of year with the responsible research and innovation and sort of the sort of group work, the challenge weeks that we do. You know, approaching little tasks is something that's really sort of fed to us. So yeah, meaningful collaboration for me is one of the most important things that we're sort of taught as doctoral students.
I would like to also add to what Neil said and what also Alistair mentioned before. As PhD students, we are pretty much taught to be adaptive to the changes in policies, changes in technology. We're pretty much stuck with our projects for the next 4 years, and within 4 years, many things can happen, and a lot of happens within climate research as well. There is a lot of new data coming in. There's a lot of new information being found out. There are policy changes. So all of that we have to kind of adapt to and work with, and then evolve our research throughout the years. So I think this is quite unique for doctoral students, that we kind of have this one project that we're working on for relatively long term. And throughout this time, we might have a plan, for example, at the very beginning of our project in our first year, but there might be some new technology that will be interesting for us that comes up and that we suddenly want to integrate into our project. So we're basically constantly adapting. Another thing is throughout all this year, we're also gaining new skills. So whenever we find a particular skill gap, we have this opportunity to actually go and receive relevant training. So this is quite a unique opportunity that actually we have to be able to work on one project for quite a long time, and as well learn all these new skills.
So I like the point about that you're focusing on a project for 3.5, 4 years. I used to work in the Earth observation industry for a few years before starting my PhD. And in contrast to that, I think a PhD is an excellent opportunity to produce a focused body of research on one thing. And you're not necessarily answering questions, answering challenges that will translate into something useful many years down the line. You're hopefully going to produce something that could actually have a real world application now, which is why I really like the idea of a PhD focusing on one thing, but also the importance of collaborations with industry as you progress through your PhD, and that kind of multidisciplinary engaging with lots of different people as you undergo your project.
Brilliant. I think you make a really interesting point at the end there, Sam. There certainly is a difference between academic research and industrial research, isn't there? And although that's not, I suppose we don't have enough time to focus on everything today, that's a very interesting point, and I'm sure a lot of strong opinions there. So as we hit the 10-minute mark, we'll have to move us on to our second question of the day. So this is perhaps one more for the academic staff we have with us here, but obviously we appreciate student contribution for this one as well. This question is, how are our CDTs designed for the future, and can CDTs such as ours fix existing skill gaps in geospatial or data science?
I'll go again. I'll foreground this. I think the way I want to respond to this is in topic form, if you like, rather than skill form. So if we think about the climate crisis and the topics or the areas that will need innovation and the great minds on, they are things like clean energy, clean transport, nature-based solutions, thinking about adaptation and resilience, both as Alistair mentioned, not just the human population, but also nature as well, and finance. And if you think about what data are required to underpin all of those topics, they're geospatial. It's basically mapping, it's knowing where things are, then being able to develop the solutions on the back of that geospatial data. So absolutely, the CDTs that we've got here today are about now, and are very much about filling those skill gaps. And as Alex mentioned, it's not a static environment. We will be moving forward, and the skills that you require will also change. But I think a lot of what we hopefully are delivering is a confidence in you, instilling that confidence to say, you know what, I've learned X, Y, Z. There's no reason why I can't then learn, A, B, C. I will respond to the demands of society, and that's certainly why I'm in the job that I do, is to basically to enable the students to fly high into the future, and I will ultimately benefit from that, right, as well society as a whole. But I think what we've got now is a real urgency that we perhaps didn't have. I mean, I was doing climate crisis stuff or climate change stuff when I was a PhD student, started 30 years ago. But I think now more people are aware of what may be coming down the line. So where you are is very, very important. So I'll stop there and hand over to somebody else.
Yeah, I'm happy to pick up the baton there. I think, thinking about this in terms of topics is a nice way of understanding, the role that you as PhD students and us as educators play in ensuring those skills gaps are filled. Because as Dorian has pointed out, as geospatial specialists, be that in the geospatial systems or the SENS CDT, we're interested in collecting data about the Earth and understanding that data about the Earth and presenting that data, whatever that data or those data, depending on how you say it, may be. And that puts us in a very powerful and interesting position as scientists and engineers and doctoral candidates, because we're in the center of so many different things. We're bringing in data from all kinds of different specialisms and integrating it together. And that's what climate change really needs, because it's such a broad challenge that is caused by so many of the things we do and impacts upon so many of the things that we do, we really need to understand how that spatial location, the shared position of the things that we care about, be they things in the natural world or infrastructure assets or different parts of society, all of those things share a location on the Earth's surface. And by having the skills to understand that, to analyze that, to visualize that, you're really in a strong position to help tackle this challenge for years to come. I mean, this, you know, are we future-proofing you? Hopefully, yes, because this is not a challenge that's going away anytime soon. And having the skills to go out into the world, be that in academia or in industry or in the you know, voluntary sector, to go and make a difference. By being able to understand spatial data and think about it and model it, you're really putting yourself in a strong position to then go and be at the forefront of this challenge. And I think the other thing that's really crucial is by being part of a CDT and being part of a cohort, you are learning that interdisciplinary view of the world too. And I think that is absolutely vital in tackling climate change. I've mentioned I was a member of the Tyndall Centre. I'm not a member of the Tyndall Centre because I'm an expert on climate change. I'm a member of the Tyndall Centre because I am a geospatial person who applies that often to climate change. And as part of that group, because it's an interdisciplinary organization, I find myself talking to economists, to atmospheric scientists, to experts in renewable energy, to people who are interested in coastal erosion. And that immersion in the interdisciplinary view of climate change is really powerful. And hopefully, as being part of a cohort of students, you're getting the perspectives of different people who are tackling different challenges and understanding how it's important to have that varied view of the world and the interdisciplinary perspective on any challenge, but particularly this big challenge of climate change.
So it almost seems that the design of our CDTs, just by the nature of their field, you feel is sort of applicable to the climate crisis, which is great for all of us. Maybe it would be time to switch to some of the students. How do you feel on this? Do you feel like you have been upskilled by your CDT?
I certainly think so. I think, I mean, the CDT was set up to address a skills gap, and that is a skills gap in lots of exciting hot topics in tech at the moment. So you've got the perfect storm of big data and machine learning, and of course geospatial, that in conjunction alongside the growing Earth observation industry in the UK, and the demand for people with those skills is not going to go away anytime soon. And it's also stuff that we're achieving things that weren't perhaps possible a couple of years ago. So lots of the new exciting things coming out with machine learning, for example. You can apply them to the pressing problems of today, while also giving us lots of skills to see what the field looks like in the next few years as well.
Yes, building on that also, apart from the technical skills, I think one of the most important elements of CDT is actually the responsible research and innovation training that we receive. Because I think nowadays in current times, we can kind of see a bit of a crisis of trust in science and scientists. So I think it's even more important that we are aware that we have to be mindful in how our research is designed and communicated. And so that is also effectively communicated to the public, so that we can actually clear out any kind of misunderstandings, any fake news that are kind of spreading around. With the power of the internet, we are actually given this opportunity to actually look into our research from the perspective of where it puts us in the society and how we can actually contribute to the society.
Yeah, sort of finishing up, I think something that we're really encouraged to do and sort of appreciate, building on what Sam said, is this sort of appreciation for emerging trends, and sort of feeding into what Dorian said. We're not just looking at the sort of traditional geospatial data that is obviously huge at sense. We're looking at emerging sort of geo-related data that really can provide new ways of looking at existing problems. And that appreciation for sort of emerging trends in geobig data and machine learning is something that we are constantly being encouraged to seek out. And I think as these problems sort of evolve and become more pressing in the coming years, that adaptability and that ability to really see what's coming is quite important.
Excellent points all around there, and good to see, I think, broad agreement across the spectrum of the panel here that I think the CDTs seem to be addressing, at least for now, the existing skill gap there. That's good to hear. Moving on to our third question. Communication is a critical skill for all scientists. Is the training we receive as doctoral students sufficient? So, Alex, this really picks up on a point you made in that last question, which was that some would say there is this crisis of trust towards scientists, particularly in certain places in the world or among certain groups, etc. I don't want to force you to deep dive into this too much, but do you think that that's kind of on us to solve as future scientists? And are we being set up for success in that regard?
Partially, yes, because in the end, we are the scientists who kind of creating the research. So it is our responsibility to make sure it is communicated properly. So a lot of them is information that is currently happening. It stems from the fact that scientists just do not communicate their findings to the public in an easy to understand way. One thing is also that a lot of the science is also published in closed access journals. So one of the great things about the CDT is that we are encouraged to to publish in the open access, to make sure that we make our data available so people can actually have a look at it and see what we've done. That is not some data that we've invented. And as well, how we also encourage to participate in outreach activities. So there's quite a lot of really nice initiatives targeted both at adults and the younger audience. And I think it's a great opportunity for us to actually get out to the people and tell them what we're actually working on in a more informal environment. Because on the other hand, we might publish all our science in the journal papers, but for a lot of people, all these words, they don't really make much sense. They don't fully understand how it's written. And to be honest, throughout the literature review, when I was reading quite a lot of papers, I couldn't understand what they actually mean. So it's actually, developing the skills as well. How do we communicate effectively? How do we make sure that we write in a way that is easy to understand and digest as well? And I think the CDT is giving us quite a few opportunities with different workshops that we can take part in. And especially if we identify a skill gap, for example, I don't know, I'm not very good at making posters, I must admit. So I'm going to go and take a workshop in poster design. And we've got all these opportunities that we can take throughout the next 3 or 4 years of our CDT.
Yeah, I think there's some really nice points in there, Alex. And I think you do realize as a scientist sometimes, reading other scientists' work, that, well, I think academics in general, we like to sometimes make ourselves sound, maybe enigmatic, I don't know, or, use language that is inaccessible sometimes because we think that gives us more authority, maybe, I don't know, but there is a problem there of communication, that when we create all of these scientific results, we need to ensure that they are being communicated to as wide an audience as possible. I think surveys often show that scientists are still one of the most trusted groups by people across society. We're up there with doctors and surgeons and people like that. We do have a platform, and because of hopefully the training you also get in a CDT of academic rigor and thinking about the way that you undertake your analysis, the way you present your results, that gives you that kudos to say, well, actually, here is some work I've done, and people trust that you've done it properly and that it's been, rigorously designed. And then the peer review process, when you come to publish, which all of you will at some point from the results of your PhD, because it's gone through peer review, that gives it that extra layer of credibility. So I think generally there are obviously parts of the population that don't trust scientists, but I think most people do. And I think that gives us a really strong voice. The key then is using that voice in the right way, and to communicate the right messages. And one of the issues, I think, because of that scientific rigor, is sometimes as scientists, we're a little bit reticent to say anything controversial. And we're always very careful to kind of hedge our language. And I think for me personally, the time has come in the climate crisis to stop doing that and be a little bit more outspoken about things like climate change, and try and tell it a little bit more as it is, because there's an urgency there now, and there's a danger that if we cloud everything in this kind of very careful scientific language, that urgency is lost somewhere in the process. So I think, yeah, we have a platform and we should use it, but we need to make sure that you guys are equipped and skilled in those communication skills. So things like writing blogs, maybe. Every time you write an academic paper, I was told this in this policy academy that I was part of a few years ago, that every time you write an academic paper, you should also write a policy-focused version of it that says what the policy makers need to take out of this bit of research, but also a blog, a kind of accessible, public-facing version of the paper that says, well, what is the research telling us, but in a less academic language. And I think that's a really good practice to get into, because it says the same thing in 3 different ways, and therefore makes your work far more accessibility and the communication of your work more effective.
Yeah, I really like that idea there. I was actually gonna jump to you there, Sam. Sorry, I cut you off. Yeah, I want to see maybe because I only know the Geospatial Systems CDT. How do you feel as a Sense student? How do you feel you've been dealt with the communication skills?
I think training's been fantastic, and it's still ongoing. One thing I would say is that I've heard a lot over the last year of how would you explain your PhD project to a stranger at the bus stop. That's a good exercise as communicating your own research. But then also communicating your own research is different to breaking down the complex issues behind the climate crisis to a stranger as well. And both those forms of communication are really, really important. The Sense CDT focuses on lots of different outreach opportunities. For example, hopefully we'll be in Edinburgh next month doing some outreach training as a big cohort, which is particularly exciting. But it's something that you learn a lot through experience. If you're not very good at communicating your research, there's a lot of practice that makes you much better. But certainly within our line of research, it's something that is really, really important to get right alongside your research.
Yeah, really, some really exciting points there. I think, Ali, the sort of idea of blogging, or something I know that Max has spoken about, is the sort of idea of having like a CDT podcast, another different way of communicating our research and making it a bit more fun, making it a bit more accessible. Streaming services make that so possible these days. So yeah, some exciting possibilities. I think when I think about sort of communication and the ways that we get our research out there, I think back to the beginning of the year, Doreen, when we were looking at impactful research. And I think something you said that sort of sticks with me is impact is the future currency of research. Not just the research that we do, but how do we really get that across? How do we make sure that the gap between the people that we are trying to affect and ourselves is sort of shortened? How do we sort of minimize that gap and really communicate what we're doing properly? And I think you sort of press the idea of stakeholders. Really, how do we communicate our research to the people that really need it? And I think one thing that's really exciting about our CDT is the sort of breadth of stakeholders that we have. We obviously have the sort of government agencies, we have the industry, and I think that variety is really important in when we do come to communicate our research. How do we do it with, as Ali said, the sort of patience, but also that urgency, that strength of that strength behind it, and getting our words across properly. So yeah, some really exciting ideas to really communicate our research.
Thanks, Neil. Good to hear that I've said something that's stayed with you. Job done. I think the key thing is that the training you receive allows you to be critical about it. in whatever platform that you're communicating, you know, we've got social media now, we've got obviously you've got your academic papers and everything in between. We've also got infographics, you know, cartoons and things like that as a way of communicating. But you still have to go through the same process of trying to work out what you're trying to say with the platform that you've got, how you're best going to say it. But probably more importantly is how you judge the effectiveness of what you've just said and the way you said it. And no matter what you do with respect to communication, those 3 points are really, really important. And the other thing is you've got to use it or you lose it. So, you know, take every opportunity you can to communicate what you're doing. And the trickiest audience are the school children. So if you, I think Alex talked about outreach. If you can outreach to, you know, the younger generation to you, then and do that effectively, then you will have done a really good job for society. And it's not easy. I like to do outreach. My sister's a primary school teacher, so whenever you know, COP26 comes up, and it had done quite a lot over the last year, she's always asked me to do a Zoom conversation with her pupils. And the questions you get back make you think about the whole situation quite differently to you know, a boring old academic who might ask you about how did you do that and what was your sample size. You know, it's a very different question that you get back. And whenever you can, take the opportunity to communicate what you're doing, not just what your specific research is on, but other people's research as well, because that's a really good way of understanding how effective their communication is as well.
Brilliant. I think that's a really strong point to end this question on there. We'll keep this final question slightly shorter than the others in the interest of time. But our question for the final question for our panel today is, how do the COP26 goals align with the goals of our CDTs? So as I said, in the interest of time, maybe if we go through the students first, just to keep this a student-focused session, and then we'll see if we get some academic perspectives in at the end as well, if we have time.
Yeah, so I think sort of, you know, starting off, the main sort of goal that pops out to me was collaboration. I think, and as I sort of said at the beginning, that's what we are encouraged to view from the very first day. I mean, I look on this call, we've obviously got, you know, Clara from economics, myself from history. You know, we are incredibly broad and diverse in the subjects that we cover, and really that's what's needed going forward. We need to appreciate, you know, all the sort of you know, varying topics that are affected by climate change. And yeah, I think it's really exciting that our CDT and the sort of doctoral process champions those and really appreciates that climate change, and to really, you know, make meaningful progress, we need to appreciate and collaborate and bring everyone together. So yeah, I think that's the sort of biggest goal that's jumped out to me.
I definitely agree as well. The CDTs are championing that collaboration amongst us as researchers, but also loads of other industries and organisations out there. Also, another goal of this COP will be securing global net zero by 2050, and you know, the work that we're doing now can very much work towards that. I think that's really important as well.
I do agree with the previous points made by Neil and Sam that collaboration is vital, and I think what makes our CDTs also very good for what makes our CDTs good for aligning with the COP26 goals is also that we are multidisciplinary. And it also will help us to work towards the goal to adapt, to protect communities and natural habitats, because we constantly work with evolving technologies, with evolving policies. As I've mentioned previously, answering one of the previous questions, we basically taught to adapt throughout our PhDs ourselves. So we're also learning how to work with the data that would help to adapt to the climate change and to the environmental changes and societal changes that come out of it.
Brilliant, great to hear those there. So specifically to go into some of the COP goals that, and this has kind of been touched on already, but for instance, securing global net zero by mid-century, that's one of them. And I think it has been mentioned by our academics already that that problem really is highly geospatial in nature. I don't know if you have anything else to say on that, or indeed on any of the other goals.
Yeah, I think the goal of the CDT really is to train the next generation of geospatial experts, and that aligns entirely with COP26, because as I alluded to earlier, to secure net zero by mid-century, we need to know what net zero means. We need to know how it's quantified. We need to know the role of reforestation in capturing carbon as a carbon sink, and we need to do that. We need remote sensing skills, and we need geospatial analytics skills. We need to understand the role of new technologies and transportation in reducing emissions. So we've got people on the CDT working on low carbon transport, but not just the tech side of that, but also the behavioral side of that. How do we design our cities to enable people to use low carbon transport, not just encourage them? And then, as I also mentioned earlier, there's not just the net zero goal, but the adaptation goal and the protecting of communities and natural habitats. How we do that is, again, an inherently geospatial question, because climate risks are a spatial phenomenon. They happen in certain places, and they'll be bigger in certain places than they are in others. They'll have bigger effects on certain communities than they have on others. And that distributional effect is because of things like income. It's because of things like what's called adaptive capacity, which is basically how well can communities respond to these changes that are coming because of climate change. And that's not only about the physical environment, although that's an important part. It's also about the social and economic environment too. So I think by training our students in the CDTs in those geospatial skills, they can align with these COP26 goals in a number of ways, and hopefully contribute towards making sure that COP26 is a success, or what comes out of COP26 can actually be achieved meaningfully in the coming decades.
Brilliant. Can I get a 30-second closer from you, Dorian, to finish off the session?
30 seconds might be asking a bit too much. No, I think what today has underlined is what the aim of these CDTs were right at the beginning. Basically, if you look on the website for EPSRC, it says, to bring together diverse areas of expertise. Tick, we can see that we've done that, to train engineers and scientists with the skills, the knowledge and confidence to tackle today's evolving issues and future challenges. Tick, we're doing that, and I think today very much underlined that. But what I really like about today is the fact that we've got 2 centres for doctoral training coming together. They're funded by 2 quite separate organisations, although both government research agencies, but with a slightly different remit. Yet that hasn't prevented that collaboration in this sense, but also I think collaboration going forward across all of the centres for doctoral training. And what the climate crisis does is gives you that hook for everyone to come together and say, right, okay, this is the grand challenge that we need to address. It's not the only grand challenge, of course, but it's the one that has really come into the fore as a result of COP26. And then we also realised that the grand challenges are somewhat interlinked as well. So we're not going to be unemployed in any sense going forward. We're going to be gainfully employed, and it's a great pleasure certainly for the academics on the panel to be here to set you, as I say, to set you off on that journey of being great contributors to society, and that's what we want.
Well, no pressure on us at all then. Well, that brings us to the end of the panel discussion today. I'd love to thank all of our panelists. Really appreciate you taking the time out of your day to do this. Thank you very much to our audience as well, anybody watching online. And also a big thank you to my colleague Clara for doing all the important stuff behind the scenes. I hope you've all enjoyed the session, and I hope you enjoy the rest